What's up, guys? This is the Round Bottom Flask, and welcome to the last leg of our video lecture series for the basic concepts on structure and bonding in the context of organic chemistry. In this video, we will discuss another theory on how the covalent bonds were formed. That other bonding theory that I am referring to is the molecular orbital theory, which was formulated by Robert Mulliken around the time that valence bond theory was also developed. Now, in the molecular orbital theory, unlike the valence bond theory, the atomic orbitals actually combine. They do not simply overlap, but rather combine in order to form molecular orbitals wherein the bonding electrons reside and now belongs to the molecule itself, and not just on the individual atoms. Now, the difference with the valence bond theory is that in the valence bond theory, the bonding electrons are localized in the area of overlap between the atomic orbitals. In the molecular theory, the bonding electrons are actually roaming around the bond, okay? Are roaming around the bond, or if the compound is large enough, if the molecular compound is large enough, all over the molecule. Now, and this postulate, this theory led to a Nobel Prize for Robert S. Mulliken, which was awarded to him in 1966. So, when atomic orbitals combine, there are two possible ways. Now, the first possible way is what we call as constructive combination. So simply, in the terms of the Schrodinger's equation, by the way, the molecular orbital theory is actually an application of the Schrodinger's equation, but Robert Mulliken applied it to covalent bonds and to molecules. Now, according to Robert Mulliken, constructive combination of atomic orbitals is simply just akin to adding the two orbitals. So since each orbital is represented by a wave function, as indicated by the Schrodinger's equation, constructive combination of atomic orbitals is simply just adding these two waveforms. Remember that waveforms has a property. It's like looks like a sine wave. And remember, I don't know if you had this in your in one of your physics classes, that when two waves add up with each other, they intensify, or they reinforce each other. So that's what's happened to the constructive combination, and that constructive combination of atomic orbitals lead to the formation of the bonding orbital, okay? A low energy bonding orbital. Now, another way of combining our atomic orbitals is through destructive combination. So this is a result of the destructive combination of atomic orbitals. So their waveforms will just actually cancel each other out, and that will lead to the formation of the higher energy antibonding orbitals. Now, collectively, this is what we call as a linear combination of atomic orbitals. And this linear combination of atomic orbitals again forms the low energy bonding and the high energy antibonding molecular orbitals. Usually, you can differentiate a bonding and an antibonding molecular orbital. The notation is this one here. You have an antibonding orbital has an asterisk. So this would look like sigma star 1s. And this is an antibonding molecular orbital. And this is a bonding molecular orbital. Sorry if the font is really small. Now, if you notice here, since in the bonding of a hydrogen atom, only the 1s orbital is involved, since the only occupied orbital that they have is the 1s. The 1s, their linear combination of atomic orbitals is head-on. So it's like a sigma bond. When it can be compared in valence bond theory terms as a head-on overlap. This one here, it's the term here is it's also a head-on overlap, but it does not. The overlap will mean that the atomic orbitals will combine together. So the head-on overlap is also termed as a sigma overlap. Now, if you see here that sigma overlap forms your sigma bonding orbital, which is just looks like a sigma bond in valence bond theory, and it's also cylindrically symmetrical, and we have the sigma antibonding orbital for the formation of hydrogen for the bonding between in a hydrogen molecule. And the sigma antibonding, there is a nodal plane between the two nuclei, which means there is no bond formed here. Okay, or yeah, sorry, cancel that term. There's a bond formed, but this one, since it is antibonding, so it's something it's hard to describe. Parang ano siya, parang it cancels out the bonding. It looks something like that. Now, fortunately, the antibonding orbital in a hydrogen molecule is not occupied, so that means it cannot contribute. It cannot affect how hydrogen atoms bond with each other in the hydrogen molecule. Whoops. So now each, just like your molecular orbital is just similar to an atomic orbital, that it can hold at most 2 electrons, and it will follow the same rules for filling atomic orbitals. So that would include your Aufbau principle, your Pauli's exclusion principle, and your Hund's rule of maximum multiplicity. So now the strength and stability of a bond in the molecular orbital theory is crudely described by bond order. So there's a formula for that, wherein bond order is equals to the number of electrons in the bonding orbitals, that is the total number of electrons in bonding orbitals, okay, minus the number of electrons in antibonding orbitals divided by 2. Now, bond order is also a rough guide to determine what type of bond is formed between atoms. So, is it single bond, double bond, triple bond, or something in between? Now, a single bond will have a bond order of 1, a double bond will have a bond order of 2, and a triple bond will have a bond order of 3. So let's have an example. Let's try drawing the bonding of an He2 molecule. So its molecular orbital would look like this. Now remember that each helium atom will hold 2 orbitals, 2 electrons rather, in its valence orbital, which is 1s, and that valence orbitals will combine to form in a sigma-like overlap to form your sigma bonding and your sigma antibonding orbital. Now, what is done here next is the electrons in the atomic or in the valence atomic orbitals is distributed among the molecular orbitals. So, following the Aufbau principle, this one is filled first, followed by this one, until maubos mo yung lahat ng valence electrons. Then, we'll calculate the bond order. So, the bond order is since we have 2 bonding orbitals and 2 antibonding orbitals, so 2 minus 2 is equal to 0, divided by 2, that is equal to 0. So our molecule with a 0 bond order means that the bond does not actually exist. Or simply saying that the He2 molecule does not exist. So let us try another example here. What is the bond order for the He2 plus molecule? Now, in this case here, the He2 molecule has a positive charge. Now, just like in the Lewis structure, in drawing the Lewis structure rather, when you you subtract one electron for one valence electron for every positive charge, and you add 1 electron for every negative charge. So before to start, we need to draw first the molecular orbital diagram for the He2 plus molecule. So in drawing the molecular orbital diagram, you first draw the atomic orbitals of the atoms participating in the bond. So for this is for helium. For one helium atom, this is the orbital or atomic orbital that will be participating in the bond. So that will be your 1s. And for another helium atom, this will be for your this will also be 1s. Okay. And then, and then you also fill it with the atomic orbitals. So we know that the electron configuration of He is 1s2, so it would look like this. And then, what you do is, since there will be linear combination of atomic orbitals, you draw the bonding and the anti-bonding molecular orbitals. Then you connect those molecular orbitals together to show that they are the result of the linear combination of atomic orbitals. So this will be your sigma, and this will be your sigma star. So we put a superscript here, which indicates from what atomic orbital did it come from. So it will be sigma 1s, and this is sigma star 1s. Okay. Then, since it has a positive charge, we subtract 1 electron. Since they are both helium atoms, it really doesn't matter where you subtract your electrons. So I will subtract it from here. Then you distribute the valence atomic orbitals participating in the bond in their respective molecular orbitals, following the same rules in distributing electrons in atomic orbitals. So that would be your Aufbau principle, your Pauli's exclusion principle, and your Hund's rule of maximum multiplicity. So we'll start from this lower energy, sigma 1s. Then we'll start from the higher energy, sigma star 1s. So in some cases, when they draw molecular orbital diagrams, they put an arrow here with a big letter E on the left side of the arrow, indicating that going up will be there will be increasing energy. So this is it just shows a qualitative graph of the energy levels. Okay. Then after that, since we have already completely filled we have distributed all of our valence atomic orbitals, we can now calculate for the bond order. So the bond order is equal to the number of electrons in the bonding or molecular orbital, which is 2, minus the number of electrons in the antibonding orbital, which is 1, divided by 2, and your bond order is equal to 1/2. So He2 plus molecule actually exists. However, this is not stable, since the bond that is formed is significantly weaker than that of a single bond. So that what it means when we say that the bond order is 1/2. So in general, there are rules that we need to follow when we're drawing molecular orbital diagrams, or in the formation of molecular orbitals. So just like in valence bonds, in hybridization, the number of atomic orbitals involved in bond formation is also equal to the number of molecular orbitals that are formed. Another is atomic orbitals with will combine most effectively with other orbitals of similar energy, or at least closer in energy with them. Next is as the overlap increases, or the way that the molecular orbitals combine, or the effectivity of the way that the atomic orbitals combine to form molecular orbitals, and the gap between their bonding and anti-bonding the energy gap between the bonding and anti-bonding orbitals, molecular orbitals that they form, will increase. That means the energy of the the energy of the bonding molecular orbital will increase, and the energy of the the energy of the bonding orbital will decrease, and the energy of the anti-bonding or molecular orbital will increase. So sorry about that. There was a typographical error in my sorry lang. Lastly, I've said that before, that they will also follow the distribution of electrons, the rules in distributing electrons in atomic orbitals. So Aufbau, Pauli's, and Hund's. So for the period 2 s block metals, their bonding is pretty much the same, except that on top of the 1s, you will also add the 2s. So for example, in lithium, both the 1s orbital and the 2s orbital involved in the bonding process. Now here, if you look at beryllium, the 1s is also involved. However, since 1s is not the valence electron, we do not include it when we're drawing molecular orbital diagrams, because usually in the core electrons, or rather the electrons in electrons that are not the valence electrons, so they are on the inner side of the atom, or the inner portions of the atom. It is expected that when these core atomic orbitals combine to form molecular orbitals, all of their bonding and anti-bonding orbitals will be filled. So the deciding factor will actually be in the valence atomic orbitals. If when they combine, will all of the bonding or the anti-bonding molecular orbitals that they form will be filled with electrons or not. Okay, so that's why in this case here, in the beryllium in the bonding of Be2, we only included the valence orbital, not 2s. Now, if you notice, just like in He2, the beryllium molecule has also a bond order of 0. So that means such molecule does not exist, or if it exists, it's not that stable. Now, when we go, when we proceed to p block to the p block elements of period 2, not only the 2s is involved, but also in 2p. Now, we have seen in the valence bond theory that p orbitals can undergo can have a head-on and a sideways overlap to form a sigma bond and a pi bond respectively. Now, the same thing also happens in the context of molecular orbital theory, wherein the p block element, wherein the one of the p orbitals will undergo a sigma overlap, and the other two of the p orbitals will undergo a pi overlap to form your pi bonds, your sigma bonds and your pi bonds respectively. Now, by convention, the z-axis is the bonding axis, or the bonds are formed along the z-axis, and so by convention, the sigma bond, it's usually the 2pz that undergoes sigma bonding. That's by convention. Other textbooks uses the x-axis as a bonding axis. Thus, yung 2px yung nag-undergo ng sigma bond. It actually depends, but in advanced inorganic in both undergraduate and graduate level inorganic chemistry textbooks, the bonding axis is usually the z-axis. Now, just like in valence bond theory, a sigma overlap, a head-on overlap, is more effective than a sideways overlap, and therefore it is expected that the sigma 2p will be lower in energy than the pi 2p. Now, the problem here is that this was not observed in the molecules, in the diatomic homonuclear diatomic molecules of the lighter period 2 elements, lighter p block elements of period 2. So, if we shown here, the one wherein the ideal molecular orbital diagram for a period 2 p block element is only observed in heavier elements from oxygen to neon, while boron, carbon, and nitrogen, in their molecular orbital diagram, it's actually pi 2p that is lower in energy than sigma 2p. So what is the reason for that? The reason for that is because that s and p orbitals, since they reside in the same energy level, the two s and 2p orbitals reside in the same energy level, their energy difference is actually quite small, and they interact with each other in a phenomenon called orbital mixing, which actually lowers the energy of the 2s orbital and slightly raises the energy of the 2pz orbital. So it would actually look like this. And since 2pz is the one that undergoes the sigma bond formation, so the sigma 2p will have an elevated energy, while the sigma 2s will have a lower energy. And if you notice, going to the right of the periodic table, the energy of the sigma 2p decreases until oxygen and fluorine, wherein sigma 2p will now be lower than pi 2p. Now, the reason for that is because as you go to the right of the periodic table, the positive charge of the nucleus increases since you increase the number of protons. Okay, and this increase in the number of protons, exert electrostatic attraction, which further lowers the energy of the orbital. So it lowers the energy of the sigma 2s more than the sigma 2p, and then it lowers the energy of the 2s orbital more than it lowers the energy of the 2p orbital. This is because 2p orbitals are farther away from the nucleus, are found farther away than in the nucleus than the 2s orbital, as seen in their radial probability distribution. It's similar to why only certain metals observe certain transitional metals observe a half-field stability or a certain configuration. So this is the reason for that. Okay, and since oxygen has a greater positive charge, since the nucleus of oxygen has a greater positive charge than the nucleus of nitrogen, oxygen will exert greater electrostatic attraction to the 2s and the 2p atomic orbital, which further lowers the energy of the 2p atomic orbital and the 2s atomic orbital. However, that decrease in energy is greatly observed more in the 2s than the 2p, since again 2s, the radial probability distribution of, since a 2s electron is most likely found closer to the nucleus than a 2p electron. So let's have an example wherein two atoms of different elements will form a covalent bond. So let's have HF. Now, this is the molecular orbital diagram for HF. Now, since in hydrogen, the 1s is significantly higher in energy than the 2p of fluorine, because it's again hydrogen is a quite lighter element than fluorine, and it does not exert that much electrostatic attraction to their atomic orbitals. Thus, mas higher yung energy ng 1s ng ng hydrogen compared to that of fluorine. Now, they tried making the molecular orbital this way. They base it from the Lewis structure of the molecular orbital. So in the Lewis structure of hydrogen fluoride, this is the Lewis structure of hydrogen fluoride. So they have seen that in the Lewis structure of hydrogen fluoride, only a single bond is formed. Okay, so in order for a single bond to be formed, the bond order should be equal to 1. So they devised the atomic orbital such that the bond order is equal to 1. So how did they do that? What they actually did here is only one of the 2p orbitals will combine with the 1s orbital. Will undergo a sigma bond with the 1s orbital, and this is also consistent with the valence bond theory. Now the non-bonding molecular orbitals, on the other hand, the other 2p orbitals rather, are non-bonding molecular orbitals. So, ang nangyari is this one is the one that will undergo a linear combination with the 1s to form your sigma and your sigma star, while these other two will remain as non-bonding molecular orbitals, which actually signify two of the lone pairs. So where does the other lone pair come from based on the Lewis structure? So it actually came from the 2s. So remember that fluorine still has a 2s orbital, which is also completely filled with electrons, and that 2s orbital became a non-bonding orbital. It did not participate in the linear combination of atomic orbitals. This is because that the 2s orbital is significantly lower in energy, that hindi siya tugma it's not a match with the 1s of hydrogen in terms of energy. Now, for the molecule NO, so this is what its a molecular orbital diagram would look like. So they try to draw the molecular orbital such that it is consistent with its Lewis structure. Now again, remember that oxygen is a more heavier element than nitrogen, so therefore its 2p orbital would be lower in energy compared to the 2p orbital of nitrogen. So when they form, so in the 2p side, when they form molecular orbitals, since the sigma 2p, since the sigma 2p will being above the being in higher energy than pi 2p will have a greater contribution, will have a more even distribution contribution from each of the 2p orbitals from nitrogen and oxygen respectively. So what they did is the 2p is a higher energy than the sigma 2p rather is higher in energy than pi 2p, and this is again consistent with what do you call this? This is again consistent with the Lewis structure. And if you notice here, since the sigma 2p is closer in energy than oxygen, that means oxygen will have a greater contribution to the formation of the sigma 2p compared to nitrogen, since it is closer to energy. Okay? And thus, that also means that the electrons at sigma 2p will spend most of its time in the 2p in oxygen rather than nitrogen, which is also consistent to the electron distribution, which is also consistent to the bond polarity of NO. Okay, so let's have a last example here. Let's draw the orbital diagram for the molecule carbon monoxide and determine rather its bond order. So we will only draw the valence orbital. So the valence orbital of carbon is 2s and 2p. Since oxygen will stabilize its atomic orbitals more due to its higher nuclear positive charge, so the 2s of oxygen will be lower in energy. So the 2s of oxygen will be lower in energy. I hope you can notice the difference. Same goes with the 2p. So when they mix, we draw the molecular orbitals. Now, in order for oxygen, for both, in order for, let's say, balance out, or either for there will be a perfect balance in the contribution of the atoms in the molecular orbital in the linear combination of atomic orbitals, we drew it such that sigma 2p, sigma 2s is higher in energy than sigma 2p. Sigma 2p is higher in energy than pi 2p. So it would look like this. This is pi 2p. This is pi star 2s. This is pi 2s. Sorry, this is pi 2p. This is sigma 2p. And this is pi star 2p. And this is sigma star 2p. Okay? Then from their atomic orbitals, we distribute them to their respective molecular orbitals. So carbon has 4 valence electrons, so 2s2, 2p2, and oxygen, the valence electron configuration of oxygen is 2s2, 2p4. Then we distribute them according to the Aufbau principle. So we have 2 electrons here, Then we distribute them. So first is pi 2p, following Hund's rule of maximum multiplicity. Then this one here. So we have used 2, 4. Then we have 2 more remaining. So that is 6. Okay. Then we can calculate the bond order. So the bond order is equals to, we have how many we have how many bonding electrons? So 8 bonding electrons minus 2 antibonding electrons in the sigma star 2s divided by 2. So 8 minus 2 is equals to 6 divided by 2, that is equals to 3. So that means there is a triple bond in the carbon monoxide, which is consistent with its Lewis structure. Okay, so that's it, guys. I hope you find this video interesting and educational, and if you do, don't forget to subscribe to my YouTube channel. And once again, this is the Round Bottom Flask signing off. See you guys.